As adults, we walk. As toddlers, we stand. As infants, we crawl. However, all of these essential benchmarks of human life would not be possible without the hip. We can contribute the ability to have domain over our own body to this essential structure. Without a functioning hip, people long for the gift of free movement and envy those with it. Hip failure is a common medical condition experienced by over 3 million people every single year. This condition is most commonly experienced by those over 70 years old. Hip failure is most often caused by a condition known as osteoarthritis, which is the breaking down of joint cartilage due to wear and tear over time. The cartilage serves as a lubricant that reduces the frictional strain placed on the ball joint of the hip. The removal of this cartilage causes the hip joint to undergo increased friction, causing damage. The goal of hip replacement treatment is to either replace the cartilage with a material of low friction coefficient in what is called a partial hip replacement, or replace both the cartilage and damaged joint altogether in a full hip replacement. Harvard Health records that over 330,000 hip replacements are conducted every single year in the United States. Out of these surgeries, the most commonly performed is the total hip replacement, as it not only serves to address current hip issues, but also secures the client's future hip health by making further bone damage a non-issue.
When we walk and during other physical activities, many forces act on the hip joint. The combination of those forces creates stress on the hip joint, which amounts vary depending on the phase of the gait cycle we're in. The gait cycle refers to the pattern of body movement during walking. There are two main phases during this cycle, the stance and the swing phase. They are further divided into 8 subphases for a total of 10. The mid-stance phase, a subphase of the stance phase, which corresponds to the period during which the foot is on the ground, is the one during which the hip experiences the most amount of stress. Consequently, we will use it as our basis for the analysis of the forces. The forces acting on the hip during the mid-stance phase are the weight of the body supported by the leg, which amount to 5/6 of the total body weight, the forces due to the muscles and the ligaments, Fm, the ground reaction forces, and the joint contact forces. To simplify, we use Powell's model for calculating the hip joint reaction force, which assumes that the force is balanced out only by the partial body weight and the force of the abductor muscle, and that it acts at the hip joint rotation center. The different forces acting on the hip are represented on a free body diagram, and we assume equilibrium. A and B are the moment arms of the forces about the center of hip rotation. Using sum of moments about that point, we find an expression for the resultant force on the hip. The joint reaction force is equal in magnitude and opposite in direction to the resultant.
The acetabular cup, which you can probably tell from its name, replaces the acetabulum. The cup is made of a very strong metal and acts as a socket for the hip. The plastic liner fits into the acetabular cup. It serves as the articular cartilage in the hip. Much like regular cartilage, it is susceptible to wear and tear and is typically the first component to fail within the hip replacement. The femoral stem is attached to the thigh bone, which is an anchor for the joint. The artificial femoral head and stem are usually made of metal, though the head may sometimes be made of ceramic. This part plays the role of the femur head and the neck.
The design choices for hip implants are heavily influenced by the physics of the hip, due to it bearing a significant amount of body weight and thus being subjected to forces of large magnitudes. Materials for the implant must have enough strength and stiffness to withstand the stresses created, while guaranteeing the necessary range of motion and biocompatibility. The sizes and shapes of the different components also play an important role. Femoral stem design influences how forces are distributed within the bone. Wide, tapered stems distribute stress more evenly, reducing the risk of bone fracture. The head size and bearing surface also play a role. Larger heads translate to greater stability, but because there's more surface, it increases contact stress. Overall, understanding the physics of the hip joint is crucial for designing hip implants that are safe, effective, and long-lasting.
The acetabular cup was designed to ensure the stability with the acetabulum while also facilitating smooth and constant contact with the femoral head. The cup was designed with standardized dimensions for easy integration with other components while also ensuring easy disassembly in case of needed revision surgeries. The cup is made of biocompatible materials such as titanium, surgical steel, or ceramics. These specific materials were chosen to reduce negative reactions while also ensuring implant longevity.
As previously mentioned, the liner is a smooth component between the cup and the head of the hip replacement. Its primary purpose is to increase the longevity and comfort of the replacement surgery by reducing friction between the two harder components. The liner is one of the most recent additions to the hip replacement assembly and is a component most often replaced due to wear. The liner features simple design for assembly with a symmetrical design that matches the concavity of the cup so that the surgeon can easily replace and align it with minimally invasive surgery. The flexibility of the liner also means that it can be easily removed and squeezed into its pocket. The liner is made of ultra-high molecular weight polyethylene, a highly cross-linked and biocompatible polymer with a high wear resistance and low coefficient of friction. It is also radiolucent, or does not block X-rays, showing its design for ease in future medical procedures. Although it is often replaced more than its metallic counterparts, design for sustainability is proven through the fact that it is a recyclable material. One way to produce the liner is through a compression molding of the polymer. After its manufacturing, it is often cross-linked to improve the mechanical properties and then sterilized for the human body. According to a 1995 PubMed study, compression molded liner shows a 2 times reduction in wear from machine liners. We will now take a deeper look at this fascinating manufacturing process. Compression molding involves placing a measured amount of material, typically in powder or pellet form, into a heated mold cavity. The mold is then closed and pressure is applied to compress the material, forcing it to take the shape of the mold. Heat softens the material, making it malleable, while pressure ensures proper consolidation and distribution within the mold cavity. This combination results in a molded part with consistent dimensions and properties. Compression molding is compatible with a wide range of materials, including thermosetting plastics, thermoplastics, rubber compounds, and composite materials. This versatility makes it suitable for diverse manufacturing needs. Designing the mold tooling is crucial for successful compression molding. The mold cavity must be precisely machined to the desired shape and dimensions, with features like vents and gates to facilitate material flow and air evacuation. After setting, the final polymer can be removed and the final product is created. Advantages of compression molding include lower tooling costs compared to injection molding, the ability to mold large and intricate parts, and excellent material distribution for uniform mechanical properties.
Though total hip replacement is a widely used procedure, there are still multiple risk factors that lead to revision surgery. Fretting corrosion is a common failure that occurs when metal from an implant begins to deteriorate. Another prevalent issue is corrosion of the implants. The presence of blood, tissue, and organic fluids in the environment of sleeve engagement was identified as the main cause of severe corrosion. Cobalt, a form of metal used in hip replacements, has been classified as possibly carcinogenic to humans, primarily if it encounters microenvironments such as the liver, spleen, and lymph nodes. To reduce trauma and recovery times, scientists are looking into less invasive surgeries using 3D printed components. The custom fit and improved grip allow for smaller incisions and easier installation. Total hip replacement has come a long way, but like all other human advancements, there is still room for improvement.